Hi, welcome to the SWAYAM course on Biomedical Instrumentation and Sensors. This is Nipun Kumar Mishra, Assistant Professor, Department of Electronics and Communication Engineering, Guru Ghasidas Vishwavidyalaya, Central University, Bilaspur, Chhattisgarh. So, the function of any sensor is to sense or measure some physical quantity and represent it into the readable form. Sensors requires some sensing element which is sensitive to that particular physical quantity. So, the interaction of sensing element with physical quantity can be in many ways depending on the element's characteristics. It can be mechanical, electrical, electromagnetic, thermal or optical, etc. So, in this module, we will see how electromagnetic property can be used to sense the normal and infected tissue in biomedical field. But before the discussion, let us see the basic characteristics of sensors. So, there are many characteristics of sensors which can be classified as static characteristics or dynamic characteristics. So, static characteristics are the characteristics which do not change with the time, and dynamic characteristics are the characteristics which changes with time. So, first we are going to discuss some static characteristics, and first characteristic we are going to discuss, that is a sensitivity. So, sensitivity represents the ratio of the change in output signal to the unit change in input quantity. So, in any sensor there will be some input physical quantity and there will be some output which is in readable form. So, the ratio of the change in output signal to the change in input quantity is called its a sensitivity. So, this diagram is representing that delta S is the change in input signal, and corresponding to that change in input signal there is delta Fs change in output signal. So, the ratio of this delta Fs to the delta S will give you as the sensitivity of that particular sensor. So, that can be represented as a slope of this input and output characteristics or calibration curve of the sensor characteristics. So, for example, there is some temperature sensor. Let us assume for 1 degree change in temperature, there is a 2 millivolt change in output. Then its sensitivity will be the 2 millivolt per degree. So, sensitivity of sensor should be high enough to develop a readable or detectable change in output signal for the smallest change in the input quantity. Another characteristic of the sensor is selectivity. So, it determines whether a sensor can respond selectively to a group of unit or even specifically to a single unit of input. Larger selectivity indicate a specific point of operation. So, this selectivity depends on application to application. In this module, we will discuss the metamaterials as a sensor. So, we will see later how this selectivity can be represented. So, it is responding to this particular band, it is not responding to the whole band. So, then it is selectivity is basically representing that it can be respond to the particular point or it can respond to the band of frequency. In this diagram we can see that sensor is responding for any particular frequency or band of frequency, and the same thing is applicable to the biosensor to respond to the specific quantity, not to the other. Suppose we are using that biosensor for measuring the blood property. So, that sensor should respond to the particular element of blood, not to the other element of a blood. Another characteristic is repeatability. So, repeatability represents that for the multiple measurement with the same sensor, whether it is showing same response again and again or not. So, our sensor should be the repeatable, it should show the same response for the multiple experiment. Another term is the reproducibility. It shows whether the same results can be reproduced with the different sensor at same operating conditions. Normally, biosensors are used for the one time to avoid the contamination. So, if we are using the different sensors with the same operating condition, then whether same results are reproducible or not, that is called a reproducibility. While repeatability is concerned for one sensor with multiple measurement and getting the same results. Another characteristic is stability. So that stability defines the ability of sensor or measuring system to maintain its standard of performance over a prolonged periods of time, or ability of a sensor to produce reproducible results for a certain period of time. It shows the robustness of the sensor or system. Another important term of a sensor is accuracy. So it refers to the degree of closeness or conformity to the true value of the quantity under the measurement. So basically accuracy is representing the how much our sensor is near to the true value. So it can be represented by calculating the relative error, and that relative error is calculated by this formula, that is given by the true value minus actual value divided by the true value. So for example, if true value of the temperature is 30 degree and our sensor is showing the reading of a 29 degree, then the relative error will be the 30 minus 20 by 30, that is a 3% error, or we can say that our sensor is 97% accurate. Another characteristic is precision. Precision is another characteristics which is very important, and accuracy and precision sometimes are used interchangeably. So precision is a measure of the consistency or repeatability of the measurement, means successive readings do not differ. Probability distribution of output should be sharp to be more precise. For example, if the true value of any temperature is 30 degree and sensor is showing the reading of 27, 27.2, 27.3, 26.9, 26.8 in 5 different readings, then these readings are close to the 27 degree, but actual reading is 30 degree. So we can say that since every time readings are close to 27 degree, then it is precise, then every time it is giving the readings nearly 27 degree, but it is not accurate because our accurate reading is 30 degree. So the sensor should be the highly accurate and it should be the highly precise also. So accuracy refers to the degree of closeness, that our reading is how much close to the true value, while precision refers to the our sensor is showing the same readings again and again. Another characteristics of the sensor is resolution. If the input or measurement to sensor is increased slowly from some arbitrary non-zero value, then output may not change at all until there is a certain minimum increment in the measurement. This minimum increment in measurement is called a resolution of a sensor. Suppose we are taking some scale length and we are measuring the length. So if there is a change in length which is lesser than millimeter, then scale cannot measure, hence millimeter is resolution or certain minimum increment required for scale. So it is a smallest increment of an input that can be detected. Suppose we are measuring the temperature and our sensor is showing the readings 5 degree, 10 degree, 15 degree, 20 degree. It means it requires the change of 5 degree for showing the output. So if in an input there is change of only 2 degree, then output will not show any change. So in this case 5 degree will be the resolution for that particular sensor. Another characteristic is a threshold, that is a minimum input value required to produce output. We have seen many times in electronic equipment like transistor that there is some threshold value. So after that value of input, output will respond. So that will called a threshold, and the same thing is applied to the sensor also, that there is some minimum input value required to produce the output, that is called a threshold value. Offset or drift, so there may be some output present when there is no input, means due to some the operating condition, due to some issues in operating condition, there is output is available while there is no input. So that is called a offset or drift. For example, if we are we are using some weighting machine and there is no weight on that particular weighting machine. Also, it is showing suppose half kg weight or 0.8 kg. Then if we are taking the weight on that particular machine, then that machine will show the measurement of that drift, that is error, plus that measurement of that particular person. So that offset or drift will be associated, it cannot be removed. It can be removed by calibrating the particular instrument before the use. Another important point is dead band. So sensor, it is representing that sensor is insensitive for this particular band, as there is no change for output for change in input in this particular band. Another important characteristics is dead band. So dead band represent that sensor is insensitive for that particular band. So that can be measured by the sensitivity curve. Suppose sensitivity is not linear in some particular band and it is stepped. In that case, the slope of this sensitivity will be 0. So sensitivity basically represents, as we have seen earlier, that sensitivity represent change in output with respect to change in input. So if their sensitivity is 0, means there is no change in output for the change in input, then sensor will be insensitive. So dead band is showing that our sensor is not responding for that particular band. That band may be the temperature range, that band may be the frequency range, that will depend on application to application. Another characteristic is drift. So that drift is basically, it is a slow variation in the output signal of a transducer or measuring system, which is not due to the change in the input quantity. So in this diagram we can see that input is not changing, input is 0, but still output is showing some non-zero value. So that is called a drift, and this drift will be associated with this particular sensor throughout. So it is primarily due to the changes in operating condition of the component inside the sensor. Another characteristic is linearity. So it indicates the relation between input and output, whether input and output curve is following the linear equation or not. So we want that our sensor should show the linear characteristics. Another characteristic is response time. Basically it is a dynamic characteristics, it is changed with time. So it is the time required by the sensor or instrument to settle down to its final steady state position after the application of an input signal. So smaller settling time represent higher speed of a response. So we want that our sensor should have a smaller settling time so that it can respond quickly. Another characteristic is range. So it is a minimum and maximum input for a sensor beyond which sensor can damage. So each sensor has some range of operation, that is called it's a dynamic range, and normally it is defined in a data sheet that the sensor should be range in some particular operating conditions. After that it can damage, or before that it cannot show the accurate results. Another associated characteristic is span. So span basically represent the difference between the maximum value and the minimum value, or we can say that it represents the difference between the full scale and lower scale value. So for example, due to some biasing, the sensor is reading from 5 volt to 20 volt. It is not showing the result from 0 to 25 volt, it is showing the 5 volt to 25 volt only. So in this case, our range will be the 5 to 25 volt, that is maximum value is 25 and minimum value is 5 volt. So range will be 5 to 25 volt, while span will be the difference of the maximum value, that is 25, and minimum value, that is 5. So span will be the 20 volt. So in this diagram we can see that our body is normally used many sensor. It can be the pressure sensor, it can be the image sensor, it can be the temperature sensor, so it can be pacemaker. So our body is basically associated or related with the many biosensors. So as we have seen earlier, that sensor consists of a sensing material, sensing layer. So that sensing material can respond to the different types of a physical quantity. It can respond to the acoustic, it can respond to the biological or chemical, it can respond to the electrical property, it can respond to the magnetic, optical, thermal or mechanical property. So if that sensing material is responding to the acoustic, then the quantity can be it's a wave, then it can be its amplitude of that wave, it can be the phase or polarization, it can be frequency, or it can respond to the velocity of the wave. If it is a biological or a chemical sensor, then it can respond to the fluid concentration. If it is a electric, then it can respond to the charge, it can respond to the voltage, current, then electric field intensity, its phase, polarization, amplitude, its permittivity. If it is responding to the magnetic, then it can be the magnetic field, then its amplitude, phase, polarization, permeability. If it is optical, then it can be responsible, it can respond to the refractive index, etc. If it is thermal, then it can respond to the temperature, specific heat, etc. Even if it is a mechanical, if it is responding to the mechanical property, then it can be the position, it can be force, it can be pressure, it can be torque. So what I want to say, that any sensing material can respond to the different types of physical quantity. The same sensing material can respond to the electric, it can respond to the thermal, it can respond to the mechanical. So in the next module we will see that we are designing some chip that is used for measuring the infected and normal cell, but that chip is showing the electrical property, mechanical property and thermal property. We can see there is a one cancer diagnosis tool, and this chip is developed by the Professor Hardik Pandya from ISC Bangalore. So this chip is basically consisting of three types of sensor. There is a piezoresistive sensor, which is representing the mechanical property of the tissue. There is a interdigitated electrodes, which is showing the electrical property of the tissues, and there is a electrode, there are two electrodes which is showing the thermal property of the tissues. So the basic concept of this tool or chip is that we are using the piezoresistive sensor, we are using the interdigitated electrode, we are using the thermistor or two electrode. So the purpose is to identify the normal tissue and the infected tissue, because each tissue has some property, some electrical property, some mechanical property, there are some uh, thermal properties also. So, we are taking some tissues which may be the infected, which may be the cancerous tissues. So, we are placing these tissues on this chip, and there is piezoresistive sensor. So, the function of piezoresistive sensor is that when we apply some pressure on this tissues, on these tissues, then its length will change. So, it will depend on the stiffness of the tissues. So, if it is affected, then it will show the different types of stiffness. If it is not affected, then it will show the different characteristics. So, based on that, we can measure the, we can identify whether it is a cancer tissues or not. Similarly, if we are placing the tissues, infected tissues between the interdigitated electrodes, so basically the interdigitated electrodes basically consists of this type of structures. So, we can see that if there is no tissues, then these electrodes are basically the showing the open circuit type of characteristics. So, its impedance will be infinite. When we are placing the tissues, then its impedance will change, and depending on the electrical properties of the tissues, impedance will reduce, and we can measure whether our tissues is normal tissues or infected tissues, because normal tissues will have the different impedance characteristics, and infected tissues may have the different impedance characteristics. As we have seen in previous slides, that the sensing element can respond to the electrical, thermal, mechanical or optical properties. So, if it is a thermal sensor, then it is showing the sensitivity toward the temperature. So, here we want to show that the sensor, which is based on the material characterization, it is based on the permittivity and permeability, then it can be used for many applications. Based on material characterization, its permittivity and permeability, it can be used for the device fabrication, like it can be antenna, it can be filter, it can be coupler, it can be waveguide, it can be used for the microwave imaging, it can be used for the biomedical applications, and the basic theme is to find the variation in the permittivity and permeability of that particular material. Based on the knowing the values of permittivity and permeability, we can classify the material, whether that material is a dielectric, whether it is a magnetic or electric. We can use this property of permittivity and permeability for many applications. So, based on the permittivity and permeability, we can apply these properties of the material for a biomedical application. So, a metamaterial is any material engineered to have a property that is not found in naturally occurring materials. So, these materials are made from assemblies of a multiple element fashioned from composite materials such as metal and dielectrics, and the materials are usually arranged in a repeating manner at scales that are smaller than the wavelength of the phenomena they influence. They derive their properties not from the properties of the base material like metal or dielectric, but from their newly designed structures. Their precise shape, geometry, size, orientation and arrangement gives them their smart properties, which is capable of manipulating the electromagnetic waves by blocking, absorbing, enhancing or bending the electromagnetic waves to achieve the benefits that go beyond, which is not possible with the conventional materials. So, we can see that in this diagram, basically the metamaterials are a artificial material. Natural materials basically represent the positive permittivity and positive permeability, and these materials are basically the dielectrics. So, they shows the positive permittivity and positive permeability. So, basically the metamaterial are the artificial material, and these materials are fabricated, are developed from the assemblies of a multiple element, and these multiple elements are the naturally available materials like dielectric or metals. So, in left hand side we can see that it is showing the just like a normal material which is made from the different types of different atoms. So, this image is showing the concept of the metamaterial. Here we can see there are three different scenario. In first scenario, the dimension of the elements are much greater than the wavelength. In second case, the wavelength of the incoming signal is nearly lambda by 5 as compared to the dimension of the material, and while in the third case, dimension of the material is very small as compared to the wavelength of the incoming signal. So, in first case, the incoming signal is capable to resolve the different element, while in the second and third case, the incoming signal is not capable to resolve the individual element. So, the concept of effective permittivity and effective permeability comes in a picture. So, let us wind up this module here. So, before ending this module, first we are going to recap what we have learned in this module. So, basically in this module we have seen that sensor have basically two types of characteristics, static characteristics and dynamic characteristics, and based on these characteristics sensor can be used and can be classified. And later on we have seen that each material can respond to the thermal property, it can respond to the electrical property, it can respond to the magnetic property. So, in this module we have seen that sensing material can also respond to the electromagnetic property, and we have seen that the concept of metamaterial, and in next module we will see that how this metamaterial can be used as a sensing for the biomedical application. Thank you.